All right, here is our Quiz 9 review. So first up, you will have a modeling problem with a horizontal shift. So here's our problem to review that skill. So assume you're aboard a research submarine doing submerged training exercises in the Pacific Ocean. At time t=0, you start porpoising, so going alternatively deeper and shallower. At 4 minutes, you are at your deepest depth, right? -1,000 meters. At 9 minutes, you're at your shallowest depth, -200 meters. Assume that depth varies sinusoidally with time. Graph and write an equation expressing your depth as a function of time. All right, so let's list our min, our max, and then find the midline. All right, so our min here, let me visualize this with you first though, because we're looking at depth as a function of time. Okay, so our min here, where it's deepest, would be down here at -1,000. Okay, our shallowest would be about here, -200. All right, so since we read things from low to high, right, here is our min, and then here is our max. Okay, the midline, if we add those two, divide by 2, if we average them, we'll be at -600. Okay, so then we need to figure out a period. Okay, so at 4 minutes, you are at your deepest depth of 1,000, -1,000. So here. Okay, at 9 minutes, you're at your shallowest depth, -200. So right here. So 5 minutes have passed. So you need another 5 minutes. So 14 minutes to get to your min again. Right there. Okay, I usually fill in the in-between spaces too. So 4 + 9 divided by 2, right? 13 divided by 2. I'd have a little notch here at 6.5. And same thing here. Average the 9 and the 14, 11.5. So here I'd be back at the midline. All right. So from 4 to 14 minutes, we run through one whole cycle. So that took 10 minutes. Okay. And then I'm just going to sketch my graph. So it looks like that. Okay. And then I usually show that it's broken because we're not starting at time =0. Okay, so then if I list out A, B, C, and D. Okay, so for A, it depends on how you view it. So if I view this as cosine, let's say I focus on this point right here. I would need to flip it. So I need to flip it here. Okay, and I see that the distance from my midline to a min or to a max is 400. So I would say -400. That negative is because of the vertical flip. Okay, for B, I'm looking at 2 pi over my period, which is 10. So pi over 5. Okay, for C, right, we have a shift. So normally this point is on that y-axis, which here is depth. Okay, so we had to move it 4 units to the right. Okay, and then here D, the midline, is down 600. Okay, so ready to build it. So I would build mine as negative 400. Okay, cosine pi over 5, parentheses, t minus 4, right, there's my 4 to the right, and then take away 600. Okay, but as we know, options vary here. So let's say that you did cosine, but you were building off of this point instead. Okay, so that point would have been 9 to the right, and there would not have been a flip. So if you had said 400 cosine pi over 5 t minus 9 in parentheses minus 600, right, that would be fine too. Just another option that works. All right, next up here. All right, a vending machine automatically pours soft drinks into cups. The amount of soft drink dispensed into a cup is normally distributed with a mean of 7.6 ounces and a standard deviation of 0.4 ounces. So here we have to go back to that 68, 95, 99.7 rule. So here, right, that is 68. So 68% fall within plus or minus 1 standard deviation of average. If I go up to the 2s, that's 95%. Into the 3s, that's 99.7%. So as I fill in the increments, I start here with the 68, divide it by 2. So 34% here and here. Okay, next, all I'm doing is taking 95, subtracting this 68%. Okay, so 95, taking out that 68, and then dividing that by 2. So here I have 13.5% in these two regions. Okay, go out to here. This is 99.7, but I need to subtract that 95. Okay, I take that 4.7, divide it by 2. Here's 2.35%. Okay, if this is the middle 99.7, that means I have 0.3% left. And if I split that in half, I get 0.15% here and here. Okay, now remember, we're also told that we have a mean and a standard deviation. So it's normal. Here's the mean. Here's the standard deviation. So if I want to mark these values here, here's my mean, 7.6. I'm going to add increments of 0.4. So here I'm at 8, 8.4, 8.8. Subtract increments of 0.4. So 7.2, 6.8, and 6.4. Okay, now I'm just answering questions based on this graphic. So what percent of cups contain less than 8.8 ounces? So everything to the left right here, or I could block all of this out of view and go through the complement, right? Sometimes that's easier. So 100% minus 0.15% would be 99.85%. Okay, what percent contain more than 7.2? So I'm looking all over here. I know that to the right of the mean is 50%. So if I add 34, I'm at 84%. okay, between 6.4 and 8. Okay, so here I'm going to add up the 2.35, 13.5, and those two 34s, and I get 83.85%. Okay, what percent of cups are within 2 standard deviations of the mean? So here to here. Well, that's just going back to our rule. That's 68, 95, 99.7. So here, this is plus or minus 1 standard deviation, plus or minus 2, plus or minus 3. So this is the middle 95. Okay, what percent of cups are more than 1 standard deviation above the mean? So where is 1 standard deviation above the mean? Right here. So if I add these guys up, that adds to 16%. Okay, now, if we have 1,000 cups that can hold 8 ounces and we load them into the machine, how many do we expect to overflow? Well, anything that's more than 8 ounces, right? It's an 8-ounce cup. So anything more than that would overflow. Okay, right? It overflows because, again, it's more than 8 ounces. Okay, we just calculated what that percentage would be. So let's look at it as a decimal and multiply by those 1,000 cups. That means 160 cups is what we would expect to overflow. All right, next up. So lifespan of tigers. So the lifespan of tigers in years in a particular zoo are normally distributed. In the diagram, the shaded region represents approximately 95% of tiger lifespans. Estimate the mean and the standard deviation, right? The mean and the standard deviation. So again, it goes back to that 68, 95, 99.7 rule. And here we're looking at 95. So these markers here represent minus 2 standard deviations and plus 2 standard deviations of average. Right? The mean should be right smack in the middle. So if I want the mean, I just need to average those two bookends. So I take 17 plus 27.8 and divide it by 2. So the mean would be 22.4 years. Okay, for standard deviation, how far apart are our data points? So we take the big number, subtract the small one. So 27.8, take away 17. Okay, you take that difference. How far apart are they in standard deviations? Right, they're 4 standard deviations apart. So I take that difference, divide it by 4, and I get a standard deviation of 2.7 years. Okay, next block of problems, we're looking at probability. So always try to reduce any fractions, and if it doesn't, 4 decimal spots. Here's a block of independent, dependent probability questions. So first, find the probability. We draw 3 consecutive face cards, right, from a standard 52 card deck with replacement. So that tells me it's independent. We're replacing as we go. So independent. Okay, and we're doing 3 consecutive things. We draw a face, another face, another face. So 12 out of 52. We put it back. We draw again. 12 out of 52. Put it back. Draw again. 12 out of 52. If I reduce this first, I'd say 3 out of 13, and then to the third power. So again, reduce if you can, and if not, 4 spots. So 3 out of 13 as a quantity cubed. So there's the decimal, and there's the fraction. I'll write both, just in case. Okay, a bag with marbles. Okay, let's read that carefully. We have 30 red, 20 blue. So we have 50 total. Okay, we're going to pick 3 marbles, leaving each marble picked out of the bag after you draw. So out of the bag. So not being replaced. This is dependent. Okay, find the probability the first marble is blue, second one is red, third one is blue. So blue, red, blue. So we start with 20 blue out of 50 total. That marble does not go back in the bag. Now we draw a red. So 30 red, but 49 total marbles. That marble does not go back in the bag. So now blue, we have 1 less than that 20 and 1 less marble overall. Okay, multiply it across. Okay, there's our decimal, there's our fraction. I'll write both. Okay, next we have 10 gallery owners, 15 painters. They attend a art convention. We're picking 3 to tour the facility at random, and we want none of them to be gallery owners. So we're picking 3 different people from a very small group of 25 total. So they're all different. So this is, again, a dependent situation. And if there are no gallery owners, that must mean they are all painters. So painter, painter, painter. So 15 out of 25. Okay, different painter, not picking the same person twice. So 1 less painter, 1 less person total. And then last pick, 1 less painter, 1 less person total. So again, we type it in. Okay, there's the decimal. There is the fraction. Always prefer a fraction, but I will give you both. Okay, one last variation of independent dependent. So here, 10% of the world population has blue eyes. We're picking 3 people at random, and we want them all to have blue eyes. Now, world population is in like 8 or 9 billion people. So if I'm picking 3 people out of that massive of a population, it stays independent, right? Because the population is massive, right? Our sample size is less, way less, than 1% of the larger population. So that's what keeps this independent. So if I'm doing 3 blue-eyed people back to back to back, I really just need 0.1 to the third power. So 1 out of 1,000, or 0.001. All right, so those were all independent. We're looking at back-to-back-to-back events. Okay, this next batch, we're looking at disjoint and overlapping events. Okay, if you like a visual, then I would say draw a Venn diagram. You do not need to use one. Okay, so large city, 40% of households have a dog. 32% have a cat. 18% have both. Okay, if we pick one U.S. household at random, what's the probability it has a cat but not a dog? So if we visualize with a Venn diagram, here's our dogs, here's our cats. Okay, 18 is both. Okay, just the dogs. So 40% minus 18, here's 22%. Okay, cats, 32% minus 18, here's 14. What are my leftovers? If I take 100% and I subtract these three, 46% out here. Okay, so remember that everything in this circle, they have a dog. Everything here, they have a cat. These 18, they have both. These 22, only dogs, no cats. Here, only cats, no dogs. And here, neither. So what is it that I want? I want has a cat, but not a dog. So I'm looking at that 14% right there. Okay, the next one has the same bones. So I'm just going to draw out the same Venn diagram. So dog, cat. Here's the 18, 22, 14, right? All percents, and 46 that are the neither. Now I want exactly one type of pet. Well, these guys have two. Here, only dogs, so that counts. Here, only cats, that counts. Both of those regions have exactly one pet. So when I add those together, I get 36. So 36%. Okay, and I said leave it as a percent, nearest hundredth, didn't even have to round any decimals. Okay, next up, same deal. These are both problems where you could use a Venn diagram or not. Just depends on how you see it. So here, we're given the probability you make swim team, 3 out of 5. Water polo, 2 out of 7. Both teams, 1 out of 4. So again, I'm going to make a Venn diagram. It's a strategy. You can choose to do it or not. So here's swim. Here's water polo. So both is 1/4. Okay. So if I want just swim, I can take that 3/5, subtract that 1/4, math frac, 7 out of 20. Only swim. Okay, water polo, 2/7. So 2/7, take away the 1/4, 1 out of 28. What about those that don't do either thing? This is neither of these two options. The whole space has to add up to 1 or 100%. So if I take 1, subtract that 7 out of 20, subtract that 1 out of 4, and subtract that 1 out of 28, here's what I'm left with as a fraction. So 51 out of 140. All right, what did I want to solve for? The probability you make neither team. So what's lovely about the Venn diagram is it's compartmentalizing everything. Both teams only swim, only water polo, neither option. So this is my solution region right in here. So 51 out of 140. Okay, next one has the same bones. So let me just draw it out one more time. So swim, water polo. Okay, I'm just going to relabel all of those probabilities. Okay, but now I'm saying, how about swim or water polo? It wants the union. So if I'm taking this from the Venn diagram, I would just add up these three spaces, right? It's already accounted for the issue of a double count. So with the Venn diagram, I just have to add up 7 out of 20, 1 out of 4, 1 out of 28. Okay, 7 out of 20 plus 1 out of 4 plus 1 out of 28. Okay, make it a fraction. So we get 89 out of the 140. Okay, let's say that I didn't want to use a Venn diagram. And I just thought, well, can't I just go to that formula? Sure. Block that out of view. Okay, swim team, 3/5. Water polo, 2/7. Subtract that overlap of 1/4. Those that make both teams are counted in the swim and water polo. We don't want to double count. So if I just use my formula, so add swim and water polo, take away the double count, you can see we are at the same conclusion. So ultimately, do it however makes most sense to you. All right, next up, Mrs. Hong threw her in a problem, talking about shoes. So Miss Hong has 40 pairs of shoes, 10 sneakers, 18 pairs of black shoes. She has 5 pairs of black sneakers. So it's giving you the intersection. Find the probability she reaches into her closet and randomly selects a pair of black shoes or sneakers. So it wants the union. So the probability of black or sneakers is equal to probability of black plus probability of sneakers minus the intersection of black and sneakers. So here I'm just plugging in. So 18 out of 40 plus 10 out of 40. But those black sneakers right here, they're counted twice. I only want to count them once. So I subtract 5 out of 40. And I end up with 23 out of 40. Does not reduce. Leave it just like that. Okay, another one. Miss Hong has 50 pairs of shoes, 20 flats, 8 pairs of patterned shoes. She has 25 pairs of shoes that are flats or patterned. It's giving you the union. Find the probability she reaches into her closet and randomly selects a pair of patterned flats. It wants the intersection. So if I lay it out the same way, probability of flats or patterned shoes equals probability flats plus patterned shoes minus the intersection, which is ultimately what we want. All right, we're just given the union, the OR. So 25 out of 50 equals 20 out of 50 plus 8 out of 50 minus x. Okay, so 25 out of 50 equals 28 out of 50 minus x. So hopefully you can see that, well, it must be just 3 out of 50 here, right? Or I could just subtract this from both sides, divide the negative. Either way, 3 out of 50. Okay, another way I could get there without the formula is just going straight to the data. So 20 flats, 20 pairs of flats, 8 pairs of patterned shoes. So if there was no overlap, the or should have been 28. But the or is 25. So the difference between that 28 and 25 is just 3. The intersection is 3. So 3 out of 50. All right. Lastly, looking at some permutation combination problems. So find the number of words, right, in quotes, you can create from the letters in tastiness. So if all those letters were different, it would be 9 factorial. But we have some duplicates, and we can't tell the difference between these identical t's. So 2 factorial, divide that out for the t's. We also have duplicate s's. So 3 factorial for the s's. Do not forget parentheses. That is essential. We end up with 30,240 words. All right. 15. Chase is making her family cheese quesadillas for dinner. She offers chicken, steak, peppers, and onions as extra ingredients. So 4 extras. How many total quesadilla options are possible? So she could have none of the extras, a plain quesadilla, plain cheese quesadilla, that's 4 choose 0, or she could have all the extras, which is 4 choose 4, or something in between. So we're really just adding up 4 choose 0 to 4 choose 4. And it's like a numerical palindrome. So 4 choose 0, 4 choose 4 are both 1. 4 choose 1 and 4 choose 3 are both 4. 4 choose 2 is just 6. This is really that 4th row of Pascal's triangle, and it adds up to 16. All right, next up. 10 students attend a performance. We have 5 Basich kids, 5 Neil Cummins kids. They're all seated in the front row. How many ways can they be arranged if we have a Basich kid in the 4th position? Okay, so let's visualize that. Okay, there's my 10 tiles. Basich kid goes in that 4th position. So we have 5 Basich kids. So it could be any 5 of them. Could be kid A, B, C, D, or E. But once we have a kid in that position, there's 9 more seats to fill. So 9 factorial for everyone else. So really 5 times 9 factorial. So 1,814,400. All right, grouped by school. So we have a chunk of Neil Cummins and a chunk of Basich. But it could be, I'm just going to draw it as a big chunk. So chunk of Basich, then Neil Cummins, or vice versa. Now, since I have a block of Basich kids together, that's really just 5 factorial. Okay, Neil Cummins, same thing. But it could be vice versa. So it could be 5 factorial and 5 factorial, but with those positions switched. So it's really 5 factorial times 5 factorial times 2. So 28,800. Okay, they alternate by school. Well, we have the same amount of Basich and Neil Cummins, so it really doesn't matter who goes first. Let me lay out 10 tiles. Okay, or, so it could be Neil Cummins and then Basich. Let me alternate all the way down. or Basich Neil Cummins. Okay, so if I focus on just Neil Cummins, 5 of them could be in that first slot, then 4, 3, 2, 1. So it's a permutation for Neil Cummins here, and over here it's going to be the same. So 5 factorial for all the Neil Cummins positions, and same for Basich. So really, it's 5 factorial times 5 factorial. And here's just the other way it could have looked. So then you see, oh, it's really just 5 factorial times 5 factorial, Basich, Neil Cummins, but times 2. It's the same as the grouping, 28,800. Okay, if we put Daisy always 6th, so here is Daisy, right? Daisy's one person. She goes 6th. That one position is locked down, and then every other seat is just 9 factorial. So 1 times 9 factorial, 362,880. Okay, they eat a snack in a circle during intermission. So circle, there's no clear start or end, right? We have one person as the anchor spot. So 10 minus 1 factorial is 9 factorial. So 362,880. All right, last 2. We have 10 kids or 10 individuals attending a seminar. 4 are men, 6 are women. A reporter selects 3 attendees to interview. What's the probability 2 men, 1 woman are selected? Okay, so here's my big fraction bar. It's a probability. Men, women, total. All right, so out of the 4 men, we're looking at all the ways we could choose 2 of them. So 4 choose 2. Out of the 6 women, all the ways we can choose just 1. Okay, and then on the bottom, out of all 10 individuals, all the ways we can choose 3. So remember that 4 and that 6 make up that 10. 2 and 1 get me that 3. So then we're just typing in, and we can save ourselves time if we can see that 6 choose 1 is just 6. Anything choose 1 is just the n value. All right, so 4 choose 2 times 6 divided by 10 choose 3. Okay, there it is as a decimal. Okay, make it a fraction, 3 out of 10. Okay, one last one. So a standard deck has 52 cards. In bridge, players are dealt sets of 13 cards. What is the probability a player is dealt a hand with exactly 6 face cards? So 52 cards, sets of 13. We want exactly 6 face cards. So what it's not saying is that those 6 cards have to come with 7 other cards. And if we have face cards first, we have 12 total, and we're going to pick 6. We need to think about all those other cards that are not face cards. So 52 minus 12 is 40. So we're going to pick 7, right? Because we need it to be a hand that is 13 cards. That's the set, right, that you are holding each time. So again, we're looking at, you get 13 cards total, 6 are face, 7 must be not face, must be other. So if I draw this out, face, not face, total. So out of the 12 face cards, we are choosing 6. And out of those that are not face cards, the 40, we're choosing 7. And then on the bottom, we're looking at, out of a total deck of cards of 52, what are all the ways we could have 13? All right, we type it in. Okay, there's the decimal. Try to make it a fraction, not going. So I'll take it to 4 spots, 0.0271. All right, have a good rest of your day.